Alrighty, chapter 11. Most people find a bit of a breath of fresh air, especially coming after chapter 7, because people treat it as a bit more of a plug and play. So this is going to be all about sequences and series of numbers. So we're going to start with 11.1, which is really just an introduction to what a sequence and what a series is. And then we're going to go specifically into arithmetic and geometric sequences and series. So a sequence is a set of numbers written in a specific order. There are two types of sequences. A finite sequence that has a limited number of numbers in the domain, something like 1, 2, 3, 4, 5, stop, versus an infinite sequence where there's an unlimited. So 1, 2, 3, 4, 5, and so on. And you can assume what the next numbers are going to be. So what we do is we can define sequences using formulas so that you can find any term in the sequence using the general formula. So for example, if you had a sequence like 2, 4, 6, 8, or sorry, not 2, 4, 6, 8, 10, 2, 4, 8, 16, we could say that the general formula is 2n, meaning that if I put any value of n into this formula, where n has to be any natural number, I can get the corresponding term in the sequence. So I'm going to write this a little bit more formalized, and I'm going to say that the general term is a sub n is equal to 2 to the exponent n. A kind of stands for term, any term in the sequence. So this with the subscript n means that the general term finds the nth term, or any term in the sequence, by using the formula. So it's defined as the expression 2 to the n. So if we want to find the first term, again, subscripts are identifiers. So the first term, we plug in n is 1, and then we solve, and we get 2. If we plug in the second term, so when n is 2, we would find that it's 4. And if we plug in n is 3 for the third term, we get 2 to the 3, which is 8. And so then if we kept going, we'd get 2 to the 4 is equal to 16, and so on. So these general terms help us find any number in the sequence. Now, usually your first term will start at 1. I showed this example because there's a question in your assignment. I think it's question number 3 and question number 4 at 11.1 where they don't start at 1. And I just wanted to show you what to do if that happens. And all you do is that instead of starting at 1, your first term would actually be when n is 2. So your first term, which is a bit backwards saying, but your first term is when n is 2. So it'd be 2 times 2 minus 1, which would give you 3. So the first term, when n is 2, right, so it's really kind of the second term, is 3. And so if it asked you to find the first 3 terms, we'd plug in a is 3 and a is 4. That would give you the first 3 terms of the sequence. So we plug in n is 3, we get 6 minus 1 is 5. We'd plug in n is 4, and we would get 7. So the first 3 terms of this sequence are 3, 5, 7. Now, it could keep going. This would probably be an infinite sequence, or you could say this is an nth partial sum, or sorry, not an nth partial sum. This is just the first 3 terms in the sequence, and you could put a bracket around those 3. It doesn't matter. It also asks you to find a is 6. Don't do anything tricky. Just literally plug in n is 6. It doesn't matter that we started at an n of 2. That gets me every single time. I always want to do something fancy. But all you do is plug in n is 6, and you get 12 minus 1 is 11. Okay, but like I said, from here on out, we're going to start where n is 1. So only when they tell you specifically that n doesn't start at 1 do you have to worry about that. Okay, so let's do another one. The next step up from this is talking about what's called alternating sequences. And so what's going to happen is that if you see something that has a negative 1 to the n as part of the general term, your sequence is going to alternate in signs. The best way to show you that is to actually show you an alternating sequence. So if I ask you to find the first 5 terms of this sequence given by this general term, we're going to start by plugging in n is 1, because that's normally where we start. So it would be negative 1 to the 1, and then the base is 1 squared. So you get negative 1 to the 1 is a negative, times 1 squared is 1, so you get negative 1. Then we find the second term. Again, my equation is negative 1 to the n, and then it's n to the 2. So then I get negative 1 squared, which is going to make this term positive. And then positive 1 times 2 squared is 4. And then we find the third term. The third term, again, you're putting in n is 3 in the two places that n is in your general formula. And we get negative 1 cubed, which is negative, times 3 squared, which is 9, and we get negative 9. And then we find the fourth term. So we get negative 1 to the 4, 4 squared. Now, because this is negative 1 to an even exponent, it comes out positive, and this would just be positive 16. So when you're finding the fifth term, you can already predict that it's going to be negative, and maybe you could predict what it would be, or you can just plug it in. N is 5, so it's negative 1 to the 5 times 5 squared. So this one's going to be negative. 5 squared is 25. All right, so that is an alternating sequence. So to make sequences alternate, you put a negative 1 to the n as part of the general term. So now let's look at how to find general terms. So these are a bit of tricky questions, and I won't ask a ton of them, but they're kind of good to explore to make you think about how you could write things as a general formula. So we're trying to find an equation, a to the n, where n can be anything. You can start it at 1 or something different. Usually we start at 1s. That will find the terms in the sequence. So you have to kind of look at patterns. So my brain right away notices that this is 4, and then it goes 16, which is 4 times 4. Then it goes 64, which if you're comfortable with your perfect squares and your perfect cubes, hopefully you're going, ooh, 4 to the 1, 4 to the 2, so I don't like it when my 4s look like 9s, 4 to the 3, maybe this is 4 to the 4. So then you could plug it into your calculator, you'd be like, oh yeah, 256 is 4 to the 4, I'm good. So what is my general term? Well, it's always 4 to some exponent n, and I'm going to start where n is 1, n is 2, n is 3, and n is 4, and so on. So since I'm not making n start at anything special, I can just leave it like that. It's known that n has to be a natural number and that it will start at 1 unless you specify otherwise. Okay, so then we look at this guy. We're trying to find the general term for this sequence, or the rule or formula, whatever you want to call it. So maybe this one you notice that it goes 1, 2, 3, ooh, back to 2, 5, 6. So maybe you're starting to think something about square roots. Maybe you're going, hey, it goes 1, 2, 3, 4 is a perfect square. The square root of 4 is 2. Ah, square root of n. Right? Where n, we start with 1, and then 2, and then 3, and then 4. Square root of 4 is 2, and then 5, and then 6, and then so on. All right, do you want to try the last one? I dare you, pause the video. My hint to you would be, and this one can be a little bit of a tricky one, but my hint to you is because it's an alternating sequence, make sure you put that negative 1 in there, right? And then do you want your first term to be positive or negative, and go from there. Okay, pause your video, give this one a go. Maybe you got it, maybe you didn't, and if you didn't, don't stress. Again, this is not a huge part of this chapter, is coming up with these general terms, because we're going to be doing geometric and arithmetic sequences where there's a formula to define the general term. Okay, these are kind of just supposed to be fun, and if you're not finding them fun, don't stress. Okay, so let's worry about the negative first. Since I want my first term to be negative, and I want this to have an odd exponent, so I'm going to make n 1, and I'm going to say it's to the n, because then if I put in 1, I'll get negative. If I put in 2, I'll get positive. If I put in 3, I'll get negative, and so on. Then I have to figure out, well, what could I put in for my equation that will get 1, 3, 9, 27, and 81? Well, I know that 3 squared is 9. 3 cubed is 27, 3 to the 4 is 81. Okay, so I can go back here and say 3 to the 1 is 3, but 1 is 3 to the 0. So how could I possibly have this as a 3 to an exponent where when I put in n is 1, I actually want 0? Well, you can put in minus 1. Okay, so if I put in 1 minus 1, I get 0, 3 to the 0 is 1. And so this is my general formula. And you might have come up with something different, and as long as when you plug in the values of n, you come up with those terms in the sequence, there's nothing wrong with it, right? They don't all have to look the same. All right, good luck with your quick check.